In the previous sections, we looked at how we can improve the storage and processing of our large language models by changing the algorithms and also looking at how we actually compute some of these algorithms in practice. We can take this a step further and look at how we're actually storing the numbers that large language models represent in a fundamental way. This process is called quantization. The way that we store numbers in modern computing is by using things like floating point 16 or 32 standards. This allocates some part of the number being stored in memory for the exponent, so that's raising some number to some power, and also the mantissa, which is how we represent the digits in the number itself. The IEEE standards have particular ways of storing 32-bit precision and 16-bit precision, and that means that it allocates those number of bits to store that particular number. These are typically stored in base 2. Google Brain, when they were developing more deep learning algorithms, also realized that storing full 32-bit precision was potentially unnecessary. They came up with the Brain Float 16 format, which is used in a slightly different way than FP16. While it takes up the same amount of space on the computer as FP16, it actually changes how the exponent and the mantissa are allocated in the number. It allows for a much larger exponent, the same as that of floating point 32, but a much smaller mantissa. The way this works is they can actually store numbers that have a very large value or a very small value, but for intermediate values, they don't pay as much attention and they lose a bit of accuracy. This is actually fine for things like deep learning, as typically the numbers that you want to pay most attention to are the weights, but also the training procedure. We have to look at the gradients. Typically very small and very large gradients are what you want to pay attention to when you're optimizing, and having this trade-off of a much larger exponent relative to the mantissa was something that paid off. And we see the BF16 standard very common now and supported by most GPU providers. However, we can take this a step even further and go beyond the BF16 standard to try and save even more space. The process of quantization takes a floating point number and turns it into an integer. It does this by first taking a look at the numbers that we want to quantize, looking at the largest number, and then finding what the ratio is of that largest number to the largest number that we could represent for the amount of space that we're allocating. In the case of an 8-bit integer, that would be the number 127. And so we look at the largest number in our floating point vector, and we take 127 and divide it by that largest number. That then gives us a quantization factor, which means that we'll take all of the numbers in the floating point vector and multiply them by that quantization factor. We'll also round that number so that we get a complete integer. That is where the source of the error typically comes from. So we can then create a quantized vector of integers with just storing one floating point quantization factor. We can then convert our quantized vector back to a floating point vector, and depending on how much precision we lost, we may end up with the same floating point vector that we started with. If we think about how a function is actually represented in any computer, it is a finite precision. There are no continuous functions that we can infinitely store in any computer. What we're doing with quantization is just taking this to an extreme level where we just distinctly take chunks of value ranges and putting numbers in those buckets. We'll see more of this in the notebook to follow, but quantization has become very important in storing these large language models on consumer and enterprise hardware. If you recall from Module 2, we looked at Laura. An improvement to Laura came in the form of the Quantized Laura. Quantized Laura, or Q-Laura, takes all of the good parts of Laura and then turns it up to 11 by quantizing the transformer itself into a 4-bit version, and we'll look at how we can create quantized versions of neural networks in the notebook to follow. It then takes the adapters and turns them into an even smaller version of their 16-bit representation, and as a final step, it also uses the CPU to store the state of the optimizer and then load that from system memory into the compute resource as it is required. This allows Q-Laura to work on gigantic large language models, but do it on small pieces of hardware. Q-LoRa is one of the most popular parameter-efficient fine-tuning methods available to date, and more innovations are being brought to the table. We've seen 8-bit, 4-bit, and even some 2-bit optimizers produced for the Q-LoRa approach. This is about as far as we can take quantization for the moment, as the errors that we get when we try to quantize a 100 billion parameter model tend to become too severe for the applications that we want. Instead, we're also going to take a look in the next section about how we can take multiple large language models and find smart ways to inference with them.